Where does the mechanical energy of a falling object go when it hits the ground and comes to a halt? The answer in a nutshell, it's converted into heat. It is also possible to turn heat into mechanical energy, as in this alcohol rocket demonstration. In the 1840s, James Joule showed that energy is conserved in these processes, and that mechanical energy can be converted into heat with a 4.186 joules of mechanical work turning into 1 calorie of heat. This fixed relation is called the mechanical equivalent of heat. Joule was so taken by the notion that, according to Lord Kelvin, Joule spent his honeymoon in Chamonix measuring the difference in water temperature between the top and bottom of the local waterfall. In this lab, we will be heating an aluminum cylinder by wrapping a string around it with a known amount of tension, rotating the cylinder 100 times and allowing the mechanical work to heat the cylinder through friction between the string and cylinder. The tension in the string is supplied by about 5 kilograms or more of weight hanging from the string. The string is wrapped 3 or 4 times around the cylinder to ensure that friction between the string and cylinder suspends the hanging weight and not some external hand tugging on the loose end of the string. Since work is force times distance, and the string travels across the circumference of the cylinder each time the cylinder rotates, then the work performed after n turns will be m times g times n times 2 pi r, where r is the radius at which the string acts from the center of rotation. The hanging mass is held by a hanger, which has substantial weight of its own. It's worth measuring the mass of the hanger since it may not be exactly 1 kilogram, as shown here. Use calipers to determine the diameter of the cylinder and divide by 2 to get the radius. When the jaws of the caliper are spread to precisely the correct width, start with the scale printed on the aluminum slider to read 4.7 centimeters, not quite 4.8 centimeters in this case. Then add another digit from the rotating needle, here 0.07 centimeters, to give 4.77 centimeters altogether for the diameter. Since you're calculating the work in joules, convert the radius to meters. The actual radius of the application of the force is the radius of the cylinder, capital R, plus 1/2 the thickness of the string. Though half the thickness of the string may seem insignificant, it can improve the results to include it. Just pinch the string with the calipers to measure its full width of a little more than a millimeter, and then divide by 2. The heat deposited in the aluminum cylinder is determined by measuring the change in temperature and multiplying the mass of aluminum times the specific heat of aluminum, 0.215 calories per gram degrees Celsius, times the change in temperature. Measure the mass of the cylinder in grams, approximately 200. A temperature-sensitive resistor is embedded within each cylinder, and its resistance is related to the Celsius temperature. Unfortunately, the relationship is not exactly linear, but a quadratic relation does quite well. The formula shown applies to resistance measured in kilo-ohms. An ohm meter is placed across the leads to the internal resistor, and the resistance is read in kilo-ohms. Notice that the leads are placed in the red and black holes of the multimeter, and that the dial is set at about 10 o'clock where ohms are read. Here we obtained a resistance of 113.1 kilo-ohms at room temperature. If your resistance is not in this vicinity, get another cylinder or check your leads. So before any work is done and the cylinder is at room temperature, we plug in the measured resistance of 113.1 kilo-ohms and get a measured temperature of 22.32 degrees Celsius. Now, with 3 to 4 turns of string around the cylinder, we turn the crank rapidly so that the weight rises from the floor, and the loose end of the string requires little or no correctional tugs. The vigorous rate at which you turn the crank will maintain the weight off the floor without touching down or hitting the cylinder stand above. Count out 100 turns carefully, since the mechanical turnstile counter may not work consistently. The entire process should take about 1 minute. After exactly 100 turns, stop cranking and quickly read the ohm meter. The resistance will be lower now, indicating a higher final temperature. Compute the final temperature. Here we obtained about 27 degrees for the final temperature. Now you have all the data needed to calculate the heat added to the aluminum cylinder. The ratio of the work in joules divided by the heat in calories is the mechanical equivalent of heat. Running electricity through a resistor is another way to produce heat. The electrical equivalent of heat is numerically the same as the mechanical equivalent of heat. If a voltage V from a battery or other power source is used to propel a current I around a circuit, then the power dissipated in the resistor, here we use a light bulb for a resistor, will be the product of I times V. If the current runs for a time t, then the electrical energy dissipated, I like that word, by the resistor will be I times V times t. We will place the light bulb in water and measure the heat deposited in the water by the light bulb by measuring the rise in temperature. The heat absorbed by the water in its plastic container is the mass of water times the specific heat of water plus the mass of the jar times the specific heat of the jar, all times the temperature change. The mass of the water will be about 200 grams, and the specific heat of water is by definition of the calorie, 1 calorie per gram degree Celsius. The jar has somewhat less heat capacity than the water, but should be included as well. If we monitor the temperature with time and plot electrical energy versus heat, then we expect a straight line as electrical work from the bulb is converted into heat energy in the water. The slope of this straight line we expect to be the ratio 4.186 joules per calorie. Determine the mass of the empty jar and zero the scale with the jar present. Fill with cold water from the drinking fountain up to the red line. The scale reads negative with no jar present, but after zeroing with the empty jar, will now display the mass of water only, about 200 grams. Put enough ink in it to make it opaque. Incandescent light bulbs are notoriously inefficient, producing less than 10% visible light and over 90% infrared radiation. But if we put the ink in to collect the visible light energy as well, this is the mass we wish to record for the water. Here we show the electrical connections. You should have your TA check your circuit before turning it on. The red side of the power supply is connected to the red side of the bulb. The black outlet from the power supply passes through an ammeter to measure current, then on to the black side of the bulb. Notice that the ammeter dial is set for about 7 o'clock, with a 10 amp maximum reading, and the yellow hole must be used for the larger currents. Place the light bulb in the water-ink mixture, and connect the voltmeter to measure the voltage difference across both sides of the bulb. The voltmeter dial is set to the 20-volt range at about 2 o'clock, and the black and red holes are used. Turn the voltage all the way down before you turn on the power supply, and then ease up the course voltage to about 10 volts. Since these bulbs are made for a 12-volt car battery, exceeding 12 volts will blow them, and it takes many man-hours to repair them. Place a container of water in the styrofoam insulator. Insert the temperature probe. Collect data for about 5 minutes as you stir steadily. Here we see the data collected by Data Studio and displayed as both a graph and a table of time and temperature. Copy this data, paste it into graphical analysis. A new calculated column is used to convert time into electrical work. Take the current, here 2.46, times the voltage, here 10.20, and simply multiply by the time variable column. Calculate a column of heat in calories by multiplying the mass of water by a specific heat of 1, and add the mass of the jar times the specific heat of the jar. All this is multiplied by the difference between the temperature variable column and the initial temperature. The graph of work versus heat will have a slope equal to the electrical equivalent of heat. Over the entire range of the data, the slope we got was about 4.3 joules per calorie.